Hi folks. Today we're going to start looking at Chapter 6, which is about trig identities, and really is an opportunity to get into the meat of what mathematics is as a discipline. So in the upper left-hand portion of the screen here, you see that I wrote in sine of 1 times tan of 1 times cotangent of 1 times the cosecant of 1. And the answer here, surprisingly, is just 1. And that made me think, what would happen if I put in a 2 for each of these? Okay, I've got a 2 for the first 3 and a 2 for the last one. Oh my gosh, it still gives me 1. And so I might think, well, what if I put in a 3? And it still says equals 1. So if we thought about this from the scientific method perspective, you might come up with a hypothesis that no matter what number you put in there, you're going to get a 1. In math, we call that a conjecture. But the problem is that no matter how many numbers I try it with, I can't prove that it's going to work for all numbers by trying individual numbers. Now, it is true in this case that there are some numbers that it's going to be undefined for because tan is undefined at, say, pi over 2. So at multiples of pi over 2, this won't exist. But for all other numbers, I bet it's going to work out. If I put in 5, still gives me 1. So I think we can all agree that the number 1 is more computationally efficient than having 4 trig functions multiplied together. And in terms of optimization, we like to have the simplest possible way of expressing something. We just want to make sure that it works all the time. Two things that are equal to each other, no matter what the input is, are called identities. So it looks like sine of any angle times tan of any angle times cotangent of any angle times cosecant of any angle, as long as they're all the same, should give us 1, as long as each of those things are defined. And that should be an identity, or something that is true all the time. Chapter 6 is about trig identities. So a trig identity is an equation that represents two equal trig expressions. These identities are regularly used in many ways in higher levels of math, and they give us different ways of expressing the same kind of quantity, sometimes more elegant, sometimes more helpful in different ways. Here are the basic ones that we know already. We know on the unit circle that tangent is y over x, and that y is sine and x is cosine. So tan of any angle is equal to sine over cosine. Really, sine and cosine are the building blocks of trig. We know that secant theta is 1 over cos theta. We know that cosecant theta is 1 over sine theta. And it also always has to have an angle. So we could call it cosecant x and sine x, but it's got to have cosine and secant and cosecant of an angle. Cotangent has two definitions. Its simplest one is 1 over tangent, but its more useful one is this one here, that it would be the reciprocal of tan, and tan is sine over cosine, so cotangent is cosine over sine. Now, you'd be provided with all these identities. They don't need to be memorized, but it's probably worth jotting them down. The notes, both blank and filled in, are in the video description to this video. All these can be manipulated, all can be squared. So if like tan is sine over cosine, then tan squared of theta is sine squared theta over cos squared theta. Our big job in Chapter 6 is going to be proving trig identities, proving that two things are equal to each other. So often in science, if you have a hypothesis, you test it, you come up with an experiment that does that, and then being able to replicate that result is really important. So you'll run an experiment, and then you'll run it again, and then make sure you get the same result, and somebody else will run a similar experiment and verify through consensus. Math is a little bit different. You don't need a bunch of experiments that each independently verify an idea and come together to form consensus. All you need in math is one ironclad proof, a showing that the general case is true. So when we're proving a trig identity, we're verifying that two trig expressions are equal to each other. And the general approach is to work each side independently until they're both equal. Or you can just work one side, turning the more complicated expression into the simpler one, or vice versa. You need to show that they're equal to each other. Now, when you're working in an equation, say that we had x plus 5 equals 7. You're allowed to do the same thing to both sides, and then you can isolate x. In a proof, you can't move across the line because you don't know that they're equal until you've reached the end of the proof. So here is exactly the situation we saw to start with. Sine of something times tan of something times cotangent of something times cosecant of something, we think equals 1. And we want to show that that's for sure true. And here's what we do. We make sort of a T-chart. Okay? And one side will say left side, and one side will say right side. And we can't cross the middle of this line. It's like it's a wall. On the right side, we had a 1. On the left side, we had sine A, tan A, times cotan A, times cosecant A. I want to show that that thing on the left is really just the number 1. So one way that I could do that is just use my definitions. I know that tangent, we see it up here, is sine over cosine. So I can replace tan with sine over cosine. Cotangent is cosine over sine. And cosecant is 1 over sine A. And if I look at all that stuff and start to cross things out, let's see what happens. Cosine, that divides out. Sine over sine, that divides out. This sine over this sine. Oh my gosh, we are left with just 1. And when we find that, we can say that the left side equals the right side. So we have proven what was given to us at the start. Sometimes people write QED, which is Latin for what was to be shown. But once we show that the left side equals the right side, then we don't have to check it for individual angles or individual values of A. We've shown that it works for every possible value of A for which this thing is defined. One of the sneaky things about proofs is that there's often more than one way to prove something. And so somebody might see the exact same question and look at a slightly different approach. Okay, they might see sine A, tan A, cotangent A, cosecant A, and say, okay, let me think about this. That's like sine A times tan A, and I'll call cotangent A 1 over tan A, because that's one of its definitions, and cosecant is 1 over sine A. And they'll differently prove that these things divide out and these things divide out, and 1 equals 1, so the left side equals the right. And that makes some people really enjoy this. They find it a little logic puzzle. The idea that there are multiple ways through it can be fun. And it can also make some people kind of despair because you say, well, how am I supposed to know what the right thing is to do? When you're trying to come up with a proof, all you can do is try reasonable things. Okay? And if they don't pan out for you, then you try a different reasonable thing. It's okay to hit a dead end. You just go back and try something different. So we have our basic identities with the definitions of sine and cosine and cosecant and secant and tangent. The other ones we can use are Pythagorean identities. And we learned from the unit circle that we could think about coordinates on it that are x and y and a radius of 1. The equation of the unit circle was this: x squared plus y squared equals 1. But the other thing that we knew was that x values on the unit circle are cos theta, where this is theta, and y values are sine theta. So x is our cos. That means another way to think of the equation of the unit circle is cos theta squared plus sine theta squared equals 1. Or this is more commonly written the other way around. Sine squared theta plus cos squared theta equals 1. That's another identity. I guarantee you that if you put your lucky number in that identity, it'll give you 1. Let's try. My lucky number is 7, so I've got sine of 7 all squared plus the cosine of 7 all squared, and guess what? It gives me 1. If you put in your lucky number, it'll do the exact same thing. It's an identity. It works for all numbers. So there's the Pythagorean identity in primary trig ratios. You can also do some neat things with it. You can come up with two alternate versions by dividing both sides by sine squared. So sine squared over sine squared would give you 1. Cos squared over sine squared would give you cotangent. And 1 over sine squared is the definition of cosecant theta. So there's just an alternate version of the same. You could also divide by cos squared. So what would that give me? Sine squared over cos squared is tan squared theta. Cos squared over cos squared is 1. And 1 over cos squared is secant squared theta. Out of these three, this is the most important one. And the other ones follow suit. In the video description below, you'll find a trig formula sheet. Some of them we haven't looked at yet, but if you go just to the bottom two rows, you see the Pythagorean identities on the bottom row, and then the other sort of definitional ones for our dark trig ratios and for tangent on the second last row. This is stuff that would be given to you for a test, but it's good for you to have some familiarity with it beforehand. So at this point we have some stuff to play with. Let's see if we can expand and maybe simplify and maybe even prove some trig identities. The first one just says expand this. So let's see what we've got. We've got sine theta plus cos theta, and it's squared, so that means it's times by itself. And so that's going to give us sine squared theta plus sine theta cos theta, as we FOIL through, plus cos theta sine theta, plus cos squared theta. That's a bit of a mess. Let's see if we can clean it up. Those two middle terms, those are like terms. That's 2 sine theta cos thetas, because the order in multiplication doesn't matter. Okay, that's a little better. Not a whole lot, though. The other thing you can notice here, though, is that you've got a sine squared plus a cos squared. Together, those make 1. That's our Pythagorean identity in blue up here. So we can use that to simplify this expression. This just means 1 plus 2 sine theta cos theta. And it turns out there's going to be an identity that goes with the other part of this, but not quite yet. More on this later. So we expanded, and we used an identity because there was an opportunity to use it. And it's definitely more elegant in the last step than it is in the second last step. We can also factor trig equations or trig expressions, and we've done that before in Chapter 4. So up top, I've basically got like a y squared plus 3y plus 2. It's just that instead of y's, they're cosines. So the top would factor to cos theta plus 2 and cos theta plus 1. Just like this, y expression would factor to y plus 2 and y plus 1. You can write them in any order. On the bottom, can we factor it? Yeah, there's a common factor of sine theta. So that would leave us with cos theta. Now if I take sine theta out of this guy right here, I'm still going to be left with 1. And once you factor, you can reduce. So at this point, these terms, or those factors rather, can divide out. And we end up with something that is computationally less intense than what we started with. It's easier to sub numbers into what we've got at the end than what we had at the beginning. If you graph both of them, I guarantee you they'll look pretty much the same. Before we move on to the next part, I just want to jog your memory on adding fractions. So if I had 2/3 plus 1, I would need to make a common denominator. And the way that I would do that is I would think 1 is just 1 over 1, and I would times the top and the bottom by 3. So it would give me 2/3 plus 3/3, which makes 5/3. That's the way we add whole numbers to fractions. Let's do that in the context of some trig. So it says express as a single fraction. So right here I have cos squared theta over sine theta plus 1, plus just a regular sine theta. So that's like secretly over 1. That's just like what we started with over here in blue, a fraction plus a whole number term, or essentially a non-fraction. So we want to make a common denominator, and that denominator is going to be the one that's over here. So of course I'll need to multiply the bottom by sine theta plus 1, but I'll also need to do it to the top, right? Just like we did right here, times by 3/3 to get a common denominator. And if I do that, I'm hopefully going to end up with a common denominator. Sine theta plus 1 plus, this will be sine squared theta plus sine theta all over. On the bottom, I'm just going to have sine theta plus 1 because I multiply this 1 by the whole thing. Oh my gosh, we've got a common denominator, so I can put them together in a single fraction. Sine theta plus 1 will be my denominator. And on top, I've got all of this. Now, I mean, that is doing what it asks us to do, put it as a single fraction. But if you're thinking about what we just looked at, sine squared plus cos squared, that's just 1. So I should be able to write this as 1 plus sine theta on top. And the bottom is sine theta plus 1. And those are really identical terms. Order doesn't matter in addition. So we could just cross them out. And it turns out that that expression that we started with was like the world's worst way of saying the number 1. And we proved it. We put it in better terms just by following some little algebraic steps. Get a common denominator, add them together, and then just keep your spidey senses ready to go here to use some of these identities. Okay, the next one, as a single fraction. If it were me, I'd be inclined to use my definitions here that cotangent is cos theta over sine theta. And you can look back at that formula sheet at any point. Plus sine theta over cos theta. You know what? I'm going to give myself some room because I know I'm going to need to make a common denominator. Plus sine theta over cos theta. Let's do some other fraction stuff up here just to jog our memories. What if I had 2/3 plus 5/2? I'd need to make a common denominator, right? And a definite common denominator is going to be all the denominators multiplied together. A common denominator in that one up there would be 6. And to get a denominator of 6, I'd have to times this first one by 2/2, and this one by 3/3. You'd have to multiply each of them by sort of what they're missing. So that would be 4/6 plus 15/6, and will get us 19/6 in the end. Same idea here. Our common denominator is going to be sine theta times cos theta, just like the common denominator up here was 2 times 3. And so we need to multiply each fraction by what it's missing. This one's missing a cos theta. And if it's missing it on the bottom, then we have to times it on the top as well. This other one is missing sine theta. Okay, so what does that leave us with? Well, it leaves us with cos squared theta plus over sine theta, cos theta, rather, plus sine squared theta all over sine theta, cos theta. And that means we've got cos squared plus sine squared all over sine theta, cos theta. Somebody is going to try and do this. They're going to try and do that and say, ha, it's just sine plus cosine. That is not how cancellation works. You can't divide out specific terms. You can only divide out factors. There is something we can do here, though, eh? We've got a cos squared plus sine squared on top. Oh my gosh, that's just the number 1. So an alternate way of writing the original expression is 1 over sine theta cos theta, which might or might not be more computationally efficient. It definitely refers back to the primary trig ratios, though, which is nice. All this stuff can be kind of overwhelming when you're first getting into it. There will be synchronous help available, so just do your best to make it through the video and then ask questions when you got them in person or on Google Meet. So we've got to make, in this one, we've got to make a common denominator. And we've kind of got the idea here. You got to multiply it by whatever it's missing. So the common denominator is going to be 1 plus sine theta times 1 minus sine theta. So this one is missing the 1 minus sine theta. And the second term is missing the 1 plus sine theta. So that's got to be on top and bottom. And when we multiply, we can think of brackets around every sort of piece of it. So what is that going to give us? Well, in the first one, it'll give us 1 minus sine theta on top. On the bottom, one of the properties of multiplying a conjugate out, that's where you have binomials with opposite signs in the middle, is you'll get 1 minus sine theta plus sine theta. Oh, those will go away. And then minus sine squared theta. So when I FOIL this all out, it's going to give me 1 minus sine squared theta. Over in the other one, it'll give me 1 plus sine theta on top. And on the bottom, it's going to give me, again, 1 minus sine squared theta. There's nothing to divide out quite yet. If you wanted to divide out, you'd have to factor, and then you'd be back where you started. But since we have a common denominator, we can add up the top terms. So 1 plus 1 makes 2. Minus sine theta, right here, plus sine theta makes nothing at all. So that's good. We've got an answer here. There are other ways we can show our answer, though. So we don't know exactly what they want as a final answer. This should get us full marks. But we might also remember that Pythagorean identity. And that 1 minus sine squared looks really fishy. All of these identities can be manipulated. So I could build a 1 minus sine squared theta just by moving the sine squared over. And oh my gosh, 1 minus sine squared theta is just cos squared. So that's prettier. And a cos squared on the bottom is the same as a secant squared on top. Because this means 2 times 1 over cos squared theta, right? And 1 over cosine theta is secant theta. So this is another way of writing it, which might be even prettier still. No fractions at all. What you consider the simplest form is kind of a matter of taste here. So let's try another one to simplify it, put it in its nicest terms. You might want to pause here and see if you can use your formula sheet to turn this into something a little nicer. For my money, I look at this and I think cosine, that's as simple as I can make cosine, sine, x, cotangent. Oh, what were the definitions of cotangent? I could write it as 1 over tan or as cosine over sine. I think I'm going to go for cosine over sine because I've already got some cosines and sines involved. And once I write that, I see if there's anything I can do that's useful. Oh my gosh, those divide out. This is just cos x plus cos x, or 2 cos x. And sometimes people ask, well, what are we really doing here, though? Are we solving an equation? No, we're looking for alternate ways to represent things that might be more elegant. And we're proving that we're doing it reasonably. We're telling the story of why it's true as we show our work. So this brings us back to the idea of proof, which is the crux of the chapter. We want to prove that these two things are equal to each other. So I'm going to make a big sort of T-chart here about the left side and the right side. And on the left side, I've got this stuff. Tomorrow we'll talk about sort of figuring out what types of techniques you might want to use each time. When I look at this, I got two things that I don't like about it. I don't like that there are fractions that are separate on the left. And I don't really like that there are ratios that are not in terms of sine and cosine on the right. You can just work one side and turn it into the other, or you can kind of have them meet in the middle. I'd be inclined to make them meet in the middle here, and I'd try and get everything to sine and cosine. But there are many ways to prove an identity, so if you don't want to do it exactly this way, that's fine. So here, if I want to put them together on the left, I'm going to need a common denominator, which means timesing this by sine over sine, and this by cosine over cosine. I do that so that I get a common denominator. Okay, whatever happens on top happens. But what I really care about is that the bottom is sine x over cos x plus, let's see, cos squared x, but more importantly, over sine x cos x. Oh my gosh, I made a common denominator. I can put them together. At the same time, on the right side, I'm going to choose to say that, okay, secant x is 1 over cos x, and cosecant x is 1 over sine x. You don't have to change the right side if you don't want to. Let's see what I'm getting over here. On the left, I would have sine squared x plus cos squared x on top, all over sine x cos x. And on the right, if I multiply that through, I'll have cos x by sine x. And now, is there anything I can do? I've got most of the marks here. Sine squared plus cos squared x is 1 over sine x cos x. Sine squared plus cos squared is 1. That's a Pythagorean identity. And then on the other side, order of multiplication doesn't matter. So I could just write it like this instead. Oh my gosh, we made the left side equal to the right side. We manipulated them both until they were both the same. If you wanted to, you could have just worked with the left, or if you're a real glutton for punishment, maybe just worked with the right and turned it into the left. Maybe you had a different way of proving this. That's great. As long as you did reasonable things, full marks. So it is a creative portion of the course. Okay, here comes another one. So you can pause and give this a go on your own, and you can just try some things. See if they help you turn one side into the other. I'll assume you've done that, and I'm going to think this through. I've got two separate fractions. I want to make it one fraction, so I need a common denominator. So I'm going to times this first one by 1 minus cos x, and this second one by 1 plus cos x. At the same time, I'm also thinking my right-hand side doesn't have primary trig ratios, so I'm going to rewrite it in terms of primary trig ratios, like sine and cosine. So 2 over cosecant squared x is 1 over sine squared x. There's sort of my next step off from my right side. Let's work it through. I'd have 1 minus cos x. And then because these are conjugates, I'd end up with 1 minus cos x plus cos x, so those are gone, minus cos squared. So 1 minus cos squared x This one here, 1 plus cos x, and then the bottom is still 1 minus cos squared x. And I can put these together. 1 plus 1 makes 2. Negative cos x plus cos x makes nothing at all. Oh, I'm close here. Okay. Because my right-hand side is looking like 2 over sine squared x. And I wonder, is 1 minus cos squared x equal to sine squared x? Let's think about that. Up here, we know that sine squared plus cos squared equals 1. Let's build that 1 minus cos squared x by moving this over. So 1 minus cos squared x would equal sine squared x. Oh my gosh. There it is. So the left side equals the right side. Okay. Not the only way to prove it, but I thought I didn't really like the fractions, and I didn't really like dealing with non-primary trig ratios. One last pair of proofs. It says use conjugates to prove. So conjugates are binomial pairs like this. And when you multiply them together, you get a squared minus b squared. They're good for changing the look of a denominator. So in this one, on one side you have cos x plus 1. On the other side you have sine x. They look different, but they might still mean the same thing. And if you graphed the two of them side by side, you'd find that they look the exact same. So that's a way to justify that they're the same. But algebraic proof is a higher bar than just looking at graphs and saying, yeah, probably. So it's telling us here to use conjugates. You can actually take your pick as to whether you're going to use the left side or the right side. Again, there are a bajillion ways to prove most identities. I'm going to work with the left side. And it's got a binomial of cos x plus 1, so I'm going to use its conjugate, which is cos x minus 1. Now, what am I going to get on top as I multiply this through? Let's think. I'm going to get sine x cos x minus sine x. All over. On the bottom, I'd get cos squared x minus 1, because if I FOIL it out, the cosines will be gone. Okay, let's see. What can I do now? I want it to say sine on the bottom. So I've got to build this like cos squared x minus 1. I'm just going to go over here and think about the identity that I know, which is this. What if I could move that 1 to the other side and move the sine squared over here? Oh, so cos squared x minus 1 apparently equals negative sine x, which is not that helpful. Negative sine squared x. If I want to simplify any further, I'm going to have to factor. So on top, sine x is a common factor. I can take it out. Negative sine squared x. And now I've got stuff that I can divide out. I'm real close at this point. I've got cos x minus 1 over negative sine x. Is that equal to the right side? Oh man, so close. Not quite though, eh? One simple way to change the sign of the denominator is to multiply the top and bottom by negative 1. So that would give you sine x on the bottom, which would be nice. And it's going to give you a negative cos x on top and a positive 1. So finally, the left side equals the right side. Again, there are other ways that you could prove this, but this is a way that works. And it did tell us to use a conjugate. So let's think about the same sort of thing in this one. The one identity you might want to be aware of here is this one that's in red, because it involves cosecants and cotangents, and this question is chock full of them. There are a bajillion ways to prove this identity. We can do it with conjugates. I would choose 1 plus cosecant x on top and bottom. And I'll just multiply through. So let's see what that'll give me. It'll give me cotangent x plus cosecant x, cotangent x, which you actually don't really need to FOIL the top out. It's not that helpful. And 1 minus cosecant squared x. From earlier, we had this. Cotangent squared x plus 1 equals cosecant squared x. This is in that formula sheet. And I wonder how we could build a 1 minus cosecant squared. Well, I could send this over here, 1 minus cosecant squared x, and send this one over here, equals negative cotangent squared x. So let's see what I'll get. I'll get cotangent x plus cosecant x cotangent x equals negative cotangent squared x. As one possible way to prove this, I'm going to factor out the top. That'll leave me with 1 plus cosecant x, which looks kind of promising. And the bottom says negative cotangent squared x. And I could divide these out. And that's going to give me 1 plus cosecant x equals negative cotangent x over negative cotangent x. And I guess lastly, to make the denominator positive instead of negative, I can times by negative 1 over negative 1. And that will finally give me negative 1 minus cosecant x all over cotangent x. We've proved that these two things are equivalent to each other. So this can be kind of overwhelming because it seems like a whole new branch of mathematics where we're proving stuff instead of just using stuff. But all of mathematics had to come from somewhere, and we hope that those rules in mathematics actually are defensible, and we really need proofs to make sure that that's true. There's practice on page 314, numbers 1, 2, 3, 4, and then 7b. I'll be around for questions, and I expect that there will be questions. I hope that you found this helpful. It's okay if it hasn't all fully been digested. We'll spend another day working on trig identities and proofs tomorrow, and then we'll have a work day after that. Good luck with the material, folks, and take care.